Good morning. I'll discuss today about the centrifugal compressor. Contents of the lecture are introduction, theoretical analysis, and derivation of pressure ratio. Then I'll discuss on slip factor. In the beginning of the course, I have discussed about a radial flow impeller. Here I'll introduce a centrifugal compressor where the flow is treated as compressible. Thus, in a centrifugal compressor, air is sucked into the impeller eye and wheeled outward at high speed by the impeller. Thus, the kinetic energy of the fluid would be increased because of dynamic action of impeller. Then, the flow is gradually reduced, increasing its static pressure in the diffuser vane and the volute casing. Thus, at the end of the centrifugal compressor, we will get high pressurized air. Look here, I have encircled a centrifugal compressor in an aero engine. Here you look, the air is first compressed by a series of multi-stage compressor followed by a centrifugal machines. Please note that per stage pressure rise in a centrifugal compressor is much higher than per stage pressure rise in an axial flow machine. Further, I have introduced here the configuration of a centrifugal impeller where you can find out that eye of the impeller is forwardly carved for the shockless entry. Here, please, this is called the eye of the impeller at the beginning, and you can appreciate that it has been forwardly carved for the shockless entry of air. After the eye, there will be radial passage followed by the diffuser vane. Here, the diffuser vanes also has been well illustrated in this figure. Thus, a centrifugal compressor essentially consists of the following three components: the stationary volute casing, the rotating impeller, and the diffuser vanes. Furthermore, I have illustrated here the schematic of a single entry and single outlet centrifugal compressor where both the views have been illustrated. In the side view, please note that the impeller is connected to the rotating shaft. One can appreciate the impeller passage where air enter axially and pushed radially outward. The frontal part of the impeller is called the eye of the impeller, and thus I have marked eye root diameter and the eye tip diameter. Thus one can appreciate the meridional path or the meridional streamlines of flow passing through the impeller. Now, the diffuser vane and the volute casing are also been indicated here. Now, if we come to the plan view, you will find the impeller where the eye of the impaler is forwardly curved for the shockless entry of air, and then air is pushed to the radial direction, which is diffused in the diffuser vane and the volute casing. I have marked or have indicated here the diffuser vane, where one can appreciate the number of diffuser vane are less than that of the impaler. You can also understand that the flow area is gradually increased through the diffuser vane and the volute casing. So if you see the volute casing, one can easily appreciate that the flow area is gradually increased, and thereby the kinetic energy of the fluid at the exit of the impaler is converted to the pressure energy in diffuser vane and volute casing. So through this figure, one can appreciate the construction of a centrifugal compressor. Furthermore, I have presented here a picture of a centrifugal impaler, where one can easily appreciate that the eye is forwardly swept. This is the eye for the shockless entry of air. Here one can understand that the eye leads to the radial path, which has been well illustrated in this figure. Furthermore, you can understand the hub also. I believe through this picture you'll be able to understand the construction of a centrifugal impaler. Unless you appreciate the construction, you will not be able to understand the analysis that will be carried forward soon. Let me explain here the function of a centrifugal compressor through the schematic of an impaler. The impaler here I have considered is radial flow, and let us assume that the impaler is rotating with an angular speed omega. Further, let us consider R2 be the exit radius of the impaler, and R1 is the mean radius at entry. Furthermore, I have illustrated the velocity triangle at inlet and exit. Here I have already told R1 is the mean section. That means it is the mean between the I tip and I root. I have already stated that the impaler vane is giving a bend at entry to allow air move smoothly into the impaler, that is, for a shockless entry. Now the question is why the impaler or the frontal part of the impaler will be forwardly swept. To answer this, I have projected a section at entry looking from the top, and I have tried to draw a velocity triangle at the section R1. Furthermore, I have stated that the air will be sucked by the eye of the impaler, hence the absolute velocity at inlet will be axial. Thus I have indicated here C1 is axial to the impaler. I have considered U1 is the blade speed at the section R1, and I have drawn the velocity triangle here as W1 plus U1 is equal to C1. Here C1 I made in axial direction. Now after drawing the velocity triangle, one can easily appreciate that W1, that is relative inlet velocity, will make an angle beta 1 with respect to tangential direction. And the blade angle at inlet is decided by the direction of relative velocity at entry. Thus, for a shockless entry, blade need to be aligned with respect to the direction of W1, and that answers why at entry the blade is forwardly curved or forwardly swept. Now let me consider the exit. I have told that here I have considered the blade is radial. Therefore, the W2, which is the relative velocity at exit, will be in radial direction. And let us consider U2 is the blade speed at exit. So I have drawn a velocity triangle at exit, that is W2 plus U2 and C2, which has been indicated in figure A. Now here if you take the tangential projection of C2, that is C theta 2, would be equal to U2. So in the ideal case, for a radial flow impaler, C theta 2 would be equal to U2. But in reality, because of slip, the relative velocity at exit would sweep back as shown in figure B, where W2 is not radial. So now if you project the velocity triangle as W2 plus U2 is equal to C2, and then take a projection of C2 in tangential direction, then you will realize that C theta 2 is less than U2. Therefore, I have stated here that in the ideal case, if you neglect the effect of slip, C theta 2 would be equal to U2 for a radial flow machine. However, considering slip, in actual case, C theta 2 would be less than equal to U2 for a radial flow impaler. I have conducted now the theoretical analysis of a centrifugal compressor. Let us consider the impaler is radial, and I have superimposed here the exit velocity triangle of a radial flow compressors with and without slip. The firm line indicates the velocity triangle without slip. That is, in this case, the W2, the relative velocity at exit, will follow the blade angle, and therefore W2 would be radial. And if we consider the velocity triangle, that is U2 plus W2 is equal to C2, and then C theta 2, which is the tangential component of C2, would be equal to U2 in this case. Now in actual case, as I have illustrated, the relative velocity would sweep back by an amount Vs, which is called slip velocity. Now, with slip, the velocity triangle at exit is considered by the dotted line, where W2 is now not radial. So if we consider the velocity triangle U2 plus W2 is equal to C2, and if we take a component of C2 in the tangential direction, C theta 2 will be less than C theta 2 without slip. Therefore, the work input per unit mass will be decreased due to the slip velocity. Now I have defined a slip factor as the work input with slip divided by work input without slip. So sigma I can write equal to U2 C theta 2 with Vs divided by U2 C theta 2 without Vs, where Vs is the slip velocity. For a radial impaler, I can write ideal work input without slip is equal to U2 C theta 2 minus U1 C theta 1. Now let me consider that inlet swell is 0 and also slip is 0. If the inlet swell is 0, that means I can write C theta 1 is equal to 0, and without slip velocity I can write C theta 2 is equal to U2. Thereby, ideal work input without slip becomes U2 squared, because U1 C theta 1 is becoming 0. Now let us consider the work input with slip velocity. So if we introduce now the slip factor, I can write work input per unit mass with slip is equal to sigma into U2 squared for a radial vane impeller. Now let me consider the frictional loss because of casing and even on the vane. So if we consider the frictional loss, we may introduce now a factor which is called power input factor P. Thus, considering the frictional loss and slip, the actual work input for a radial flow impeller can be written as P into sigma into U2 squared, where P lies in between 1.035 to 1.04. Let me derive now the expression for pressure ratio of centrifugal compressor. The compression process that's occurring in a centrifugal machines has been illustrated here in TS diagram. Let us assume P01 and T01 be the total pressure and temperature at inlet to the impeller, and P02 and T02 be the total pressure and temperature at the exit of the impeller. Similarly, P03 and T03 be the total pressure and temperature at the exit of the diffuser. So, the compression process will be non-isentropic. So a dotted line, as I have indicated here, connecting P01 and T01 to P02 and T02 illustrates the compression that's occurring within the impeller. Similarly, T01 and P01 and T03 and P03, this on this point, if we connect by another dotted line that represents the compression, including the diffuser. Furthermore, please note that there will be no energy added within the diffuser. Thereby, T02 must be equal to T03. Now, difference between T02 and T01 will be decided by the work input in the impeller. Now, if we draw a vertical line representing isentropic process, then the intersection between P02 and the vertical line represent T02S. So T02S minus T01 indicates isentropic temperature rise within the impeller. Similarly, intersection of P03, this constant pressure line, and the vertical line from T01 and P01 indicates the point where the temperature is T30S. So that means T03S minus T01 illustrates the total isentropic temperature rise in the compressor, including the diffuser. Furthermore, difference between T02 and T02S indicates the impeller loss, and thus the difference between T03 and T03S indicates the overall loss. How can we indicate the constant pressure line P2, which is the static pressure rise at the exit of the impeller? From here, if we draw a vertical line, I'll get T2, where the difference between T02 and T2 is given by the quantity C2 squared divided by twice Cp. Thus, illustrated here both isentropic and non-isentropic process occurring within the machines. With respect to these discussions, I have illustrated here that the stagnation temperature rise across the whole compressor T03 minus T01 must be equal to the stagnation temperature rise across the impeller T02 minus T01, considering that there is no energy input to the diffuser. Hence, I can write T03 minus T01 is equal to P sigma U2 square divided by Cp for a radial impeller. Now let me consider the isentropic efficiency of a compressor. Here I will consider the overall isentropic efficiency. So overall isentropic efficiency is defined as a ratio of isentropic temperature rise to actual temperature rise, that is T03S minus T01 divided by T03 minus T01. From this expression, I can write T03S divided by T01, that is ratio of isentropic temperature rise, is equal to 1 plus eta C into T03 minus T01 divided by T01. From this expression, let me put the value of T03 minus T01. Thus, I can say T03S by T01 is equal to 1 plus eta C into P sigma U2 square divided by Cp into T01. Now I can express the pressure ratio with respect to stagnation temperature rise. So thus P03 by P01 is equal to T03S by T01 to the power gamma by gamma minus 1. That means P03 by P01 is equal to 1 plus eta C into P sigma U2 square divided by Cp into T01 whole to the power gamma by gamma minus 1. So this is the expression which illustrates the pressure ratio in a centrifugal compressor. Now one should understand that the pressure ratio increases with U2. So it's a function of U2 and also eta C, that is efficiency. So I have indicated here how the pressure ratio increases with respect to U2. That's a strong function of U2 because it's U2 squared. So this figure illustrates the pressure ratio versus blade speed, where blade speed has been non-neutralized with respect to inlet stagnation sonic speed. So I have expressed U2 as U2 by A01, and y-axis is the pressure ratio. So this figure indicates that as U2 increases, the pressure ratio increases, and it's a function of efficiency also. Now on a practical limit, the blade speed is limited to 500 meters per second considering centrifugal stress. Beyond that, the centrifugal stress would be out of the limit. Hence the pressure ratio per stage is limited to 5. Let us consider now the flow through the centrifugal impeller as indicated here. And here also I have illustrated the velocity triangle at the exit, where U2 plus W2 is equal to C2. And as the fluid passes through the impeller, the enthalpy will rise. Just H2 minus H1 illustrate the static enthalpy increase as the fluid will pass through the impeller. Thus the work done per unit mass flow rate, W, being the Euler work, can be given as H02 minus H01, where H02 be the total enthalpy at exit and H01 be the total enthalpy of fluid at inlet. So H02 minus H01 must be equal to U2 C theta 2 minus U1 C theta 1. So thus from this relation I can write H01 minus U1 C theta 1 is equal to H02 minus U2 C theta 2 is equal to I say, where I remains constant throughout the impaler. Therefore, in general, from this relation, I can write I is equal to H0 minus U into C theta. H0 can be written as H static enthalpy plus C squared by 2. So I is equal to H plus C squared by 2 minus U into C theta. Now from the velocity triangle, I can write C squared is equal to CR squared plus C theta squared, where CR is the radial component of C and C theta is the tangential component of C. Furthermore, I can write CR squared is equal to W squared minus W theta squared from the velocity triangle, where W theta is the component of W in the tangential direction. So I can write now I is equal to H plus half within the bracket W squared minus W theta squared plus C theta squared minus U C theta. Now again from this velocity triangle, I can write W theta is equal to U minus C theta. So I can write I is equal to H plus half within the bracket W squared minus U minus C theta whole squared plus W theta squared minus U into C theta. Now you can expand U minus W theta whole squared. After expansion, you will get the relation as I have indicated here as I. You look, C theta squared and would cancel out, and also U and C theta would cancel out. Thus, the I would be, hence I can write I is equal to H plus half W squared minus half U squared. Again, H plus half W squared is equal to H0 relative. H0 RDL is the relative total enthalpy. So I is equal to H0 relative minus half U squared. Thus from this equation, furthermore I can write H2 minus H1 is equal to half U2 squared minus U1 squared plus half W1 squared minus W2 squared. Now this bracketed term half U2 squared minus U1 squared represents the contribution of change in enthalpy because of Coriolis force, and the other term, that is half into W1 squared minus W2 squared, indicates the effect of deceleration within the impaler. So thus, static enthalpy rise will be because of Coriolis force and because of deceleration of flow within the impaler. I'll discuss now about the slip factor. Let me consider a radial flow impaler as indicated by a schematic, which is rotating with angular speed omega. And flow, you may consider the meridional streamlines of the flow that is passing through the impaler. Now, relative to the impaler, the fluid has a vorticity of minus twice omega, which is opposite to the rotation of the impeller. Thus, because of this vorticity, there will be induced streamline, which is called relative AD, as I have indicated here. Now, due to the formation of this relative AD, the flow will slip back by a magnitude of Vs. Now, if you consider, suppose let us consider the through flow passing through the impeller passage. Now, if you superimpose this streamlines, that is meridional streamlines, and this relative AD, you would appreciate that there will be a slip by an amount Vs. So in reality, the flow relative velocity will slip back by the amount of Bs, that is slip velocity, because of the relative AD. So I have indicated here the velocity triangle at the exit of the impeller with and without slip. So velocity triangle which has been drawn by the form line is without slip, that is U2 plus W2 is equal to C2. And the velocity triangle which is drawn by the dotted line is with slip, that is U2 plus W2 dash equal to C2 dash. Now C theta 2 dash must be equal to less than C theta 2. Hence, the work input is reduced because of slip velocity. And I can write from the velocity triangle that without slip C theta 2 is equal to U2 minus CR into cot beta 2. Beta 2 is the blade angle. And with slip I can write C theta 2 is equal to U2 minus CR cot beta 2 minus Vs. Therefore, the slip factor is given by sigma is equal to U2 minus CR cot beta 2 minus Vs divided by U2 minus CR into cot beta 2, which can be projected as sigma is equal to 1 minus Vs divided by U2 minus CR into cot beta 2. Now, one of the earliest and simplest expression for the slip velocity was obtained by Stodola. He assessed the expression for slip velocity by approximating a solid body-like rotation with a constant angular speed omega while inserting a cylinder at the outlet of the impeller. So let me consider a radial flow machine where beta 2 be the blade exit angle and S be the pitch. Now the cylinder is inserted at the outlet of the impeller so that the cylinder is exactly fixed to the exit, and if you imagine now the rotation of the cylinder, then it will create a velocity which is the Vs, slip velocity. Thus, if we know the S being the pitch and beta 2 is the blade exit angle, I can write D is the diameter of the cylinder as D is equal to S into sine beta 2. Therefore, Vs equal to half omega into S into sine beta 2. Now we know S is the pitch, is nothing but 2 pi R2 divided by N. where R2 is the exit radius of the impeller and N is the number of bends. Therefore, I have written here the expression of Vs is equal to half omega twice pi R2 divided by N into sine beta 2, which can be written as pi into U2 divided by N into sine beta 2. Hence, the slip factor can be stated as sigma is equal to 1 minus pi U2 divided by N into sine beta 2 divided by U2 minus CR into cot beta 2. Now I can divide both numerator and denominator by U2. So I'll get sigma is equal to 1 minus pi by N into sine beta 2 divided by 1 minus phi 2 into cot beta 2, where phi 2 is the flow coefficient based on exit condition, that is phi 2 is equal to CR by U2. Now for a radial impeller, beta 2 is equal to 90 degree. So cot beta 2 is equal to 0 and sine beta 2 is equal to 1. Thus, this expression becomes sigma is equal to 1 minus pi by N, where N being number of the bend. The value is close to the theoretical value when the number of the blade is 8 or more. Just you please note that this simple expression is very close to the exact theory when the number of the blade is more than 8. Several refined solutions for the slip velocity have been obtained by Bushyman. One such relation for slip velocity is given by sigma is equal to 1 minus 0.63 pi divided by N over 1 minus phi 2 into cot beta 2. For a radial flow impeller, beta 2 would be equal to 90 degree. Thus, for a radial flow impeller, this relation would be sigma is equal to 1 minus 0.60 pi divided by N, N being the number of the blade, which can be approximated as 1 minus 2 by N. Thank you for listening.